Yeah? Okay. I think this is us. Perfect. Good morning. It's a pleasure to actually come and present what is hopefully an exciting evolution in our industry to you. I am Marcus Blight. I'm application engineer for Sennheiser, working out of the UK. We are part of, or I am part of, a global team, 25 people, near enough, who are here to look after you as end users from the technical perspective, not necessarily from the sales perspective. You might be familiar with my colleague, Jonas Nesby from Denmark. He is my counterpart working in Norway, working in Denmark, but also covering Norway. We are the same business unit, so I get to come and talk to you today because he's on another show. So when we think about wireless links, what is it that we are using? Well, currently, most systems are analog. It's the easiest way of transporting audio in the frequency domain. We have audio wobbling around, we inject it into a local oscillator, we shove against the frequency modulation, and literally turn audio amplitude modulation into frequency modulation. It takes little to no time. It offers the quickest way of getting audio into the RF domain, at which point we travel at the speed of light to our receiving source. Everything works beautifully. The disadvantage to analog, of course, is sonics. We have to fit within a very finite window because spectrum regulations stipulate we can only deviate 200 kilohertz within our block. So we have to compress, we have to use companding schemes. Therefore, sonic degradation is at play. So from 2012, we at Sennheiser released a digital solution, and this was off the back of investigation into digital technologies starting in around 2002. And at the time, you think 2002, we were analog for everything in the audio industry. The flagship console at the time was the XL4, which was released in 2004. Digital consoles were only just starting to become an evolution. And digital wireless was also part of this. So 2012 was the first proper digital wireless solution that kind of worked efficiently, and that was 9000 series. And off the back of this, we've had various different versions with 6000 series, DX, etc. Other manufacturers have also brought out solutions using data now and transmitting a physical sampled audio to our receiving source. The advantage with modern technology or with modern chipsets, of course, is we can continually add features. We can evolve on this, and that's why our lines, I've drawn the digital option going up slightly because we are, with firmware, able to add more features. Whereas with an analog system, you're kind of stuck in the world that you are in. Unless you start changing physical circuit design, you're not going to make any changes. This sonically sounds really weird to me up here, but maybe it's the same for you, I don't know. So, yes, 2012, the guy who made 9000 series, Jan Waterman, very clever man, he quite proudly has told me recently he has done 2 products in his time at Sennheiser, 9000 series and what is now Spectera. He's been there like 25 years. He's only done 2 things. But at the end of 9000 series, Jan and Sebastian sat down and started looking into what is the next problem to solve with our wireless links. And actually, the biggest problem we have is stability now. We can make audio better by using a digital solution. We learned that back in 2002. What can we do to make stability better? And this is what has founded a WMAS evolution. So WMAS technology, we've started shouting about in 2023, but this has actually come from a whole long line of work and development to find a solution to a problem that didn't really exist until we started to actually delve deeper into the data. So our WMAS timeline actually started in 2013. This was the eureka moment of finding a solution to a problem. That then started a whole lobbying exercise Because if we're now saying we want to use more spectrum, we want to start changing the way in which people applicate their wireless systems and using broadband channels, like we're using with other devices, we need to have a regulatory change. So this is where, back in 2014, we wrote a draft documentation for ETSI, which became a modification to the harmonized standard. So the harmonized standard was modified back in 2016, or the reference was added in 2016, 2017, with other manufacturers then eventually joining to say, actually, yes, WMAS does have a worth, and we could use this in the PMSE sector. After that harmonized standard was changed, in 2018, this is when the European regulatory bodies removed that 200 kilohertz limitation. Because up until now, we've had to stick in the 200 kilohertz window, because that's what the regulators have stipulated. Now that we can do cleverer things with emission masks and holding more data in a broadband carrier, we needed to have the spectral limitation released. So 2018, that happened in Europe. That was the start. This then created a whole lobbying against global regulatory bodies, with the last one more recently being the FCC in America, accepting WMAS technologies in multiple variants, because Sennheiser was saying wider carriers, less power, better spectral density reuse. Counterparts, sure, because you're sat here, we're asking for more transmission power and less bandwidth. Both arguments that kind of stipulate the same thing, in a way that if you're going to have less in-band power, you have potentially, with a wider carrier, you have better stability in the frequency domain. With a slightly smaller carrier, you have less stability, but by putting in more power, your actual fading margin ends up being about the same. But still, what was it that we were trying to fix? Fading stability of our links was the problem. And when we talk about fading, what are we referring to? Well, our systems today are transmitting omnidirectionally. I'm wearing a belt pack now, right? This is an omnidirectional antenna. It's radiating in all planes. And free field, we have no obstacles. We can go, theoretically, with a narrowband link over 300 meters, quite happily, without any interference. When we get inside, this changes, because we now have reflections. These reflections cause phase cancellations. What we're doing with a narrowband system is playing a singular tone. You take a speaker, play a 1K tone, that's your wireless link, right? The more tones you play, the more frequencies you have on air. You then end up with a multi-tone carrier, which potentially then harmonizes, creates intermodulation, ends up being this whole thing we have to try and manage. So, singular carrier reflecting within a space will ultimately, at some point across a room, cancel. Therefore, we end up with a fade or a notch. How do we counter this today? Well, rather than putting out one antenna, we put out two, right? Diversity becomes our second chance. The better separation you can put between your antennas, the better the stability of your diversity network, the better chance you have of catching your signal. You're now listening in stereo. Yeah? But if we were to visualize this within a room, a Ricean curve kind of does this, we have fairly severe undulation points, which is of course going to change day by day, frequency by frequency, venue by venue. There is never a fixed recommendation for antenna spacing. All we can say is, as long as you're at least a wavelength apart, theoretically, that's enough to have enough chance of seeing the different signal. 2 meters minimum is always going to be better, because you're physically putting zonal separation then. Now, if you go to a theater application, putting 2 antennas at the portal, yes, might be a wavelength apart, but if you can put one downstage, portal side, and one mid-stage, you're going to end up with a much greater chance, because you've actually given a clear line of sight through maybe other obstacles as well. You might have bits of scenery that are flying in. With the WMAS system, we now started to look at how much spectrum do we need to occupy to change stability from putting lots of antennas around in a diversity network to pushing this into the frequency domain. And this is where we get into the reference that sits in the harmonized standard now of having a coherent RF channel. In order to have a coherent RF channel, you have to have at least 2 megahertz, because that's enough spectrum to have channel coding sat all the way across. So you have the same message across the entire band. With our investigations, we found that in order to remove the fading undulations, you need to have at least 6 megahertz. So the argument for having 6 megahertz is purely stability, because we're now playing pink noise. We have a broadband tone on air that's carrying all the way across it the same message. If a portion of that message becomes compromised through a fade or a notch or an interferer or whatever, the message still exists there somewhere else. If you're going to say frequency diversity, to pick out a name in a room here, branding, then it's like 300 channel frequency diversity, because the same message is little narrowband spikes all the way across. So what you can see on the right-hand side of the screen there is looking at 200 gigahertz, 1 megahertz, 2 megahertz, 6 megahertz, what happens in the frequency domain until it kind of plateaus. A 6 megahertz carrier is 30 times more stable than a 200 kilohertz carrier. So in terms of diversity, you could say it's 30 versity in 6 meg, or if you go to 8 meg, it's 40 versity in 8 meg, because the wider the tone, the more spectrum density we have. So massive advantage in stability. And actually, this is still just about working up here with from the antenna that's literally plonked on the stand, on the table, down a couple of floors. So that's the first advantage. The other advantage to now pushing into a broadband carrier is in forward propagational peak energy. We are taking our 50 milliwatt carrier, and rather than having this in a finite block and firing it hard with this massive undulation margin, fading margin that we're trying to counter for, because I think all of us as manufacturers, product manufacturers at least, aren't telling the end user, is the meters that we show you is the very bottom of the scale. The point at which you start to see the meters fluttering is kind of a warning to say you are now on the edge of the operational system. Whereas what's actually on air is typically neg 30 down to neg 60, 30 dB of window that we don't show you, no information. Because why would you need to know? There's so much power there. By taking the 50 milliwatts peak energy and pushing this now into a block, we've significantly reduced the forward throw, but we still have the same stability over our coverage area. And I think the easiest way to think of this is, if you were to do the maths on a 50 milliwatt carrier, free space, you could quite easily get 400 meters. And you're looking at me blankly now like, what? No, never. Absolutely. We could float over towards that tower. My sales director was saying earlier something to do with an old airfield. If we threw an antenna out towards that tower and put another antenna at the other side, we could do a point-to-point link absolutely fine with 50 milliwatts. You don't need 2 watts to get over to there. If you want 2 watts on it, then you'll get out to Oslo somewhere. No, absolutely no need for it. But that's assuming that we are point-to-point completely in line. If you were to take a carrier that's transmitting from here and walk that distance, you probably will at some point, 100 meters, 150 meters, start to get hits, start to get interference because of this fading undulations. We're hitting the floor. But standing perfectly still, yes, mathematically, it does work. By pushing into the block, we now have, yes, significantly better stability, but also less forward energy. So a WMAS carrier that is 6 meg or more, as you start to increase the actual amount of spectrum being occupied, so the range is theoretically going to drop. But the stability of that coverage is 40 times more stable, meaning that the reuse of spectrum becomes a lot quicker. Yes, there's an argument for saying, oh, but you need 6 meg. Yes, but only for my venue. You're next door, you can use the same frequency if you want. You're on a festival field, I'm not going to see you. If you're far enough away to not hear the PA, there's no hope that my carrier is going to get out there, unless you start to do range extension and use the abilities of the system to do multiple antenna nodes. And that's why you have that flexibility built into a Spectera solution. So in essence, a WMAS carrier can potentially see some interference from other people. It can deal with it, it can suppress it, I'll talk about how in a minute. but it's not going to push as much energy back in the opposing direction. So if we do have narrowband carriers coming into our space, like up here, there's currently narrowband systems on air, these will most likely be propagating way down into, in fact, that probably explains the random carriers I was seeing earlier. Are you tuned like somewhere down towards the bottom of the spectrum? He's looking at something else, not listening to me. Are you tuned somewhere down towards the bottom of the spectrum here? What's your frequency? I could have just looked on the belt pack, couldn't I? What is the frequency here? Yeah, so this carrier we are seeing downstairs, whereas I am just on the edge of operational range of the WMAS system up here. So yeah, visualizing a little bit easier, conventional systems will traditionally go a lot further, but be really unstable, whereas a wider band system is significantly more stable, but doesn't necessarily go as far unless you do range extension. If we look at the harmonized standards, there's or at least the reference documentation that Sennheiser submitted back in 2014, we're talking about a generic overuse of a WMAS system. And this refers to these diagrams. Not particularly pretty, but if you do delve through the information, this is what you'll find, where it's suggesting you have a node, singular base station, that has all your devices connected to it, and the stipulation within that reference documentation is that all of these portables have to be polite. What this is saying is any device that is connected to a system has to remain off air until it is connected to its master. The theory behind this is essentially what's happening with Wi-Fi. We're not connected to the Wi-Fi until the Wi-Fi says it's there, right? If you turn your Wi-Fi router off, your mobile isn't going to connect to it because it physically isn't on air. The mobile knows that you have a Wi-Fi network at home, and it's going to try and find it when you do get into your house, like it searches for every Wi-Fi network. But unless it sees the physical carrier, it's not going to connect. So that's where this theorem comes from. So all devices are looking for a beacon, and if that beacon is physically on air, our carrier is on air, then everything within the antenna network follows and tracks to that system. The other stipulation is a WMAS system should or could, not should, definitely could, be capable of carrying bidirectional communication, but also potentially bidirectional audio. This makes it a little bit vague because WMAS is an enabler. As a whole, the term multi-channel is an enabling technology. There are many ways that it could be used. Now, turn this down because that is getting slightly annoying now. We could say use the Shaw approach, again picking on you because you're in the room, which is multiple carriers within one mask. Same thing is one carrier, but it's not bidirectional. Doesn't matter, it's still a WMAS system because it's still a singular carrier. The technologies that we're implementing, which is slightly different, are three. TDMA being the first. This is exactly how mobiles work. This is exactly how Wi-Fi nodes work. Everything lives within a time slot. This resource grid is 16 slots by 8 frames, giving you 128 resource points. These resource points enable us to have, via TDD, time division duplexing, bidirectional audio. Also, interleaved with this, bidirectional control. So where you would have traditionally a separate antenna node, something else, a Zigbee link, whatever, it's integrated within the carrier. The final technology is OFDM, and this is where the channel coding comes, and actually this technology is sort of taken from digital television. Nothing is new with any of these. It's just the implementation, the gelling of these technologies is a new approach. This OFDM layer is where we get the stability across the channel coding, because essentially we have 300 channels, narrowband frequencies, all transmitting exactly the same message. The advantage to breaking things into time slots as well is, of course, only one thing is ever occupying a channel at a time. So it is a true single carrier solution because we are only actually transmitting in one slot from one device at one time. Also meaning that as part of this transmission cycle, we can build in slots where nothing transmits at all. These slots, which we're calling silent slots, enables us for the first time in any system, there's a lot of firsts, but first time in any system to actually every 8 milliseconds listen to the noise floor. We are turning off the carrier, like you do before a show. What's the noise floor change? Have the little whizzy lights that the kids have walked in with change the noise floor. You don't know until you turn your transmitters off and look at the RF meters. In this case, it's automatically doing it, automatically suppressing as much interference as it can every 8 milliseconds. So yes, every device is potentially using a singular carrier, a singular frequency, and that can be seen as a scary thing, but every device is also auto-suppressing for any sort of interference. It can cope with narrowband interference. And the actual forward propagational, as we've just said, doesn't go as far, so the likelihood is we aren't going to be affecting anybody else if they are affecting us, if that interference is low level. So when we think about a traditional microphone system, what would we need to do to get a microphone from me to the console and a feed from the console back to me? Well, today we have two separate frequencies which are on in the RF domain at some degree, and we have our control layer that's via infrared, unless you have a separate control node of some other form. A Sennheiser WMAS implementation allows you to have all of these features integrated within the singular carrier. So the carrier that we're putting on air contains bidirectional audio in those time slots in the resource grid, but also the bidirectional remote control. So once you are paired into the system, you are forever connected to that base station, and if the frequency simply moves, then all your devices will move with it. Now you might be sat here thinking, hang on a minute, this is just like mobile data and this is 5G, and wasn't there a whole lobbying against 5G? Well, yes, you could say 5G and 5G records was kind of looking at similar technologies and similar ideas, and we were a big part of this. Biggest problem with any of these technologies is latency. We don't have in any mobile communication bidirectional link fast enough time slots. The implementation that sits within the Spectera solution is actually 16 times faster than 4G. We're transmitting in 60 microsecond packets, whereas 4G is a millisecond transmission. Yes, the resource grid is slightly bigger for a 4G network, but actually we can transmit in much smaller cycles because we don't need as much stability to the carrier because we're not throwing it as far. So what this means is, no, 5G was never the solution. The best option for us to go forwards is to stay the same. So the show must go on really with the harmonized standards, staying in the same spectrum, and this is where the lobbying has come from over the last, well, literally 10 years in trying to go against regulatory bodies and keep our spectrum in the same place. So overall, if we say what is WMAS, or at least the Sennheiser implementation of WMAS, it is spectrally efficient in that we are allowing a much more spectral density to the singular carrier because we have this whole resource. The whole thing is flexible in the assigning these resources, and we'll go into that in a minute. There's less fading margin because we have the stability across the frequency domain now. We're taking diversity from antenna network to frequency domain. There's less power spectral density because we physically don't throw as far, so the reuse rate of the spectrum is a lot quicker. And the bidirectional elements that are enabled via TDD and TDMA is actually an industry first in many ways. So there's a bunch of technical fluff. What does it mean for us? Well, today we have these narrowband carriers on the left-hand side. Nice and equidistantly spaced, because it's a superlinear system, everything is good. On the right-hand side, and this is going to start flashing colors, so if anybody is triggered by flashy things, please look away, it's not too bad. But on the right-hand side, you can see we are now flashing through each of these colors in turn. Every device is taking a go. Now the other thing to think about here is, this is a bit like a conversation. I am currently one person talking to you. I am one time slot sending a message. If we all went around the room and you said your name, you're all taking your turn to say the message. Overall, the noise that's generated is 1. I'm louder because I'm out of a PA, but overall, we are all saying the same thing at our own level because we might be different distances, etc. If you're also generating at the same time, that's a narrowband system today. And that's where potentially you could have interference, you could have intermodulation, you could have harmonic because you have very similar tones in your voice. It becomes difficult to dictate what everybody's saying. So that's the other advantage here. We are keeping the overall density a lot lower. And the TDMA opens up a resource grid that we can now use to add on top or to utilize into our link modes and our audio modes. And this is exactly why we have offered link modes, because for you as an applicator of wireless, there are a few considerations that you probably have every time you put a wireless link on somebody. It needs to be of a certain audio quality. You're going to care about some people more than others. Probably the person that's paying your check, you're going to give better audio quality to. The person who is your backline guy, you probably don't care about. I don't know, maybe you have a different relationship with your touring parties. But latency is a big consideration for a lot of people. Battery runtime, potentially in theatre applications, could be a consideration too. Concerts, as long as it does 3 hours, probably fine. Channel quantities, how many channels do you need to get on air? These are all very important variables. Latency, though, comes up time and time again. And actual latency budget for an average singer is around 4 milliseconds. You could say it goes up to 7. The average person is probably 7. The average tuned-in singer is probably around 4. Because you have bone conduction, you have your head voice, and if you have anything that's coming back to you at a slightly different time, that's going to create a phase change in your head, which is where today maybe you are taking a load of low-mid out of a vocal mix and you're listening to it as an engineer like, this sounds horrific, but actually to the singer, it is going to sound right because they already have that in their head. They already have the effect. By adding more time, adding more latency, your head voice now goes from inside your head to halating. It starts to come out in front of your head. And this is where latency becomes super important. So we haven't stuck you in one fixed mode. You can choose by the resource grid, link by link, how to utilize your system. So you could have a link mode that sits down in the bottom of audio quality, and when we say the bottom, it's 6K quality. It's the same codec, essentially, so it's not bad. I welcome you to come and have a listen. It's definitely way better than anything you've heard in the analog world. But yes, potentially you could have 64 links in the lowest latency, but you could go all the way down to 0.7 milliseconds in a link. The counter effect, of course, is depending on which codec you use, depends on how much data you end up with. You either compress the data, end up with less data, means that you can send more in one go, more of a message in one go, or you don't compress the data, you end up with loads of data, and you have to use up more time slots. You shift your data into the, I would say frequency domain, but it's physically into the time slots now. The nice thing about this, of course, is we can now be entirely flexible and say, lead singer, we care about, we give them the best audio quality, the best RF robustness, they get the lowest latency, everything is great, and your crew, you give them a mode that's 2.7 milliseconds, the worst one, because actually that's fine. They don't need to reference anything that's them playing, they just need to get good audio quality and hear it reliably. We have built, with the aid of our friends at Soundbase, a tool to help with this, and it's not very visual on there, but I did make 2 examples yesterday, just to sort of try and explain how we can utilize the resources within Spectera. And essentially, both of these options are using the same amount of RF resource. We're putting on air all of the resources all the time. The time slots are always on air, regardless. It's just if the data is physically loaded to them or not. In the example on the left-hand side, I have put 16 microphones, 16 in-ears in the link density mode, and 8, is that what I've done? Yeah, I've done 8 in-ears in the live stereo mode and 16 microphones in the live link density mode. And that is used one RF resource, one 6 meg or 8 meg block. in the example on the right-hand side, I've said, well, maybe we've got a singer that needs lower latency, so they're one link mode at 0.7 milliseconds. There's 8 band members that are taking 1.6 milliseconds, and one backline tech that's in 2.7 milliseconds. But then I've also put in a couple of mic modes that are in 1.6 milliseconds for lead singers, and a couple of 3 live link density link modes for brass and maybe a BV. Yeah, it's entirely flexible to your needs, which is actually making it quite difficult for us to market. And that's exactly why this tool exists. It's online, tools.soundbase.app. You don't have to put the other bit there. I just copied it across because I thought give you the full URL. But tools.soundbase.app will take you to a whole suite of tools where you can go into the Spectrum mode planning, Spectera mode planning, and look at how you could utilize one RF carrier. The base station itself can actually process 2 RF carriers. So the fact that we have this amount of resource within one, theoretically, that one new box, if you've seen anything about it, and we'll go into what the actual product is in a minute, can process 2 RF carriers. So it could theoretically do this twice. But I think we need to sort of visualize what this means for us today against what the Sennheiser WMAS implementation could offer. This is essentially a today against tomorrow, if you like, side-by-side example, with that first option, as I showed you with the mode planning tool, of 16 microphones at the same latency as those microphones are, 2.7-ish milliseconds, and 8 IEMs connected within one RF carrier. The other advantage, of course, to this implementation is one antenna can do the job of 3, potentially, because bidirectionality exists within the RF carrier, and of course we have bidirectional audio at the same time. We've drawn on here handhelds because we do see Spectera as an ecosystem which will grow. Today there is the body pack. Tomorrow there could be a handheld. Not tomorrow, but soon. Soon enough, hopefully. And then, yes, one RF carrier becomes everything potentially for a show. Are there any questions at this point? I don't want to, I know this is being streamed as well, isn't it? We can come back to it, but I just want to stop before we go into product. No? Okay. So what do we have within Spectera as a physical product set? Well, first of all, the bidirectional body pack. Another first, one device, pretty small. Here, my hands sort of size. I have small hands. Which has a couple of unique features. First of all, headphone amp is impedance matching. So it's got 4 levels of impedance matching to change current and voltage drive according to the load that you attach to it. The antenna is auto-sensing to the frequency that you are transmitting and will change the ground plane impedance to match whatever that range is. So a UHF device can work from 470 to 694. We have left a small SAW filter window out in the middle because currently legislation in Europe stipulates that we have radio astronomy and a few other bands, so we've left out 608 up to 630 currently, but at least we can find a window somewhere within 470 and 698 if policy allows. The screen is e-ink display. We took that from EWDX because we found that it was successful. And the battery is the BA70, which going forwards becomes one battery for all. This cell will be the cell. We don't want to go into this world of having multiple charges. We did it, right? We feel the pain. It's annoying. You've got different batteries for different things. One battery does the portfolio. That's the goal, which can be charged via charging options like the L6000. You have the dock. That's downstairs if you want to come and have a look at it. And also the corporate options of being able to stick it into a desktop charger as well. We've got a little 2-bay charger if you're trying to do fly rigs. It's, has to be lithium, but at least there's a few options for it. Still has to be lithium though, because the whole transmission scheme is current driven. We need a lot of current and reliably, so that's why we offer rechargeables only in this solution. And I think that's very similar for other manufacturers. So that's part one. Part two is the antenna. The antenna is a DAD, and I don't think the Germans saw the funny side of this when they did it, but a DAD is literally the master of the house in this case, and sits at the front end of the RF domain. So the little box that's sat on the side of it is the transceiving node. Between the DAD and the base station is data. There are no RF elements inside the RF box, which is like, what is it then? Well, we'll come on to that in a minute. This has two frequency variants. So both the belt pack and the antenna have two frequency variants of TV UHF, as we just said, 470, 608, 630, 694, and the 1G4 frequency variant. Both of these options can run off the same base station at the same time, as long as you have a separate RF channel for them, which is fine because we have two RF channels within the base station. Antennas are powered over Ethernet, PoE, powered over Ethernet, and via CAT. Obviously limitations then become up to 100 meters, but as long as you stay layer 1, you can go into not switches, none of that nonsense, because latency is important here, right? But as long as you stay layer 1 and you stay point to point, then you can media convert up to 4 kilometers. And we're currently going through a few options for that. But applicating the antennas is literally one antenna as a zone now. So we're actually thinking about this more as a deck deployment than as a traditional narrowband deployment. It's a bit weird. I've done a few TV tenders recently, and like, this is wrong. I'm putting in 3U and 12 antennas and covering 96 channels across the site, because it is literally antenna nodes sort of meshing off of each other. Into the base station, from the front, boring. Sorry, it's a black box. It's got a fan on the inlet. That's it. Right? Little screen, you can set the IP. Nothing else. On the back, much more interesting. 2 power supplies, kind of has to be, because this is potentially your gig. Same as a console, same as a stage box. No, it's another single point of failure, but we're kind of getting used to that now. 4 antenna sockets, which are, again, flexible for your needs. So we could have one of those RF resources. If we took one of the examples that I showed you earlier, we could have one RF resource split to 4 antennas, and at that point you could say it's 4 versity, if you really want to, or 4 zones. So if you really need to do a main stage, a B stage, a C stage, a back stage, then we throw some network cables out, and that all sits within the singular RF carrier, and then every device can roam everywhere. External word clock, because, not just because, it doesn't need to be, but it seems valid in the broadcast world. Control, I think we understand. And then on to the SFPs. These SFPs will allow you to do in release coming later, and this won't be an additional fee, it's included in your purchase, the ability to cascade up to 8 base stations, where you could share either antenna or audio resources, but also, as a secondary option, potentially do a full fallover to a second base station. So if you are in a show critical situation, broadcast live, whatever, you could run 2U simultaneously, duplicated with duplicated antenna networks, separate power supplies, the lot, and then they're sharing the resources between the two. And if one did fail for whatever reason, then the second one will just seamlessly take over. Yeah. And then onto the audio connections. Dante is a Brooklyn card in the box. We went away from embedded. We did embedded with DX. That's fine, but you can't go below a millisecond on the Dante latency there, so potentially we're now adding more latency to a chain. The Brooklyn card is the only way of getting below that. So the Brooklyn card offers you to go to 0.25 milliseconds. The disadvantage using a Brooklyn card we found in development, and this is sort of why it took so long in some ways, because it has been like literally 12 years of development. Ordinate don't guarantee operation below 0 degrees. So in colder climates, this could become a problem. We guarantee operation down to -15, but the Ordinate card doesn't, so we built a little heating capacitor around it to warm it up. So as the device boots, it warms up the ordinate card and makes sure that the internal temperature is at 0 before it starts COM with the Dante card. Then we have 2 slots. They are slots for a good reason, because we love standards as an industry, and maybe there will be more standards in the future, who knows. At least offers some flexibility to modify the connections in the future. Currently we have 2 options, both MADI BNC and MADI multi-mode optical. Is multi-mode the right decision, is the question? Yeah? No? Somebody's saying no? Single mode, possibly? Yeah? Okay. Possible, but we went multi-mode because common denominators. Same with going Dante, common denominators, because if you really need to do AS67, it is possible. Not great, I know, not the same as using a Zeeman chipset or something, but it is still possible for the broadcast world. Each one of these connections are completely sample rate independent. So when what we're thinking about this box as is a audio converter now. As I just mentioned, there is nothing RF inside this RF box. It's purely taking audio data from these connections, converting it into our audio transmission via either a 96K or a 48K transmission scheme, and SRCing the audio in and out of these different interfaces. So from the input side, sending something to a body pack, we have to select our source, be that Dante, MADI 1, MADI 2. From the output side, we can broadcast the microphone, physical input from this body pack, to all 3 at the same time. But because it's completely asynchronous, ASRC'd, then we can actually connect at individual clocks and individual sample rates from each of these connections and not have any sort of jitter or nonsense going on between them. So it can become a split at the same time, essentially. In terms of device control, this can all be done via LinkDesk, which is brand new software, no more WSM. We're also integrating into Soundbase, because we acquired Soundbase back in September. Device control and offline editing and everything will be available there. And if you come and see us downstairs, we're currently running the web UI, which was the development back end, but we thought, well, actually, this makes perfect sense to the average user because it's literally IP address into a browser, no software required, you have access to everything. Via an iPad, via a phone, or whatever, it can be done an access point at that point. So overall, WMAS is the technology that is the enabler. We are at the forefront of driving this, along with competitors, and Spectera is our take on what we could do with the technology. What this technology has enabled is bidirectional digital IEMs and microphones, full system flexibility in audio, quality, RF links, stability, link-by-link dependent, not system-wide, full remote control as you found with other products, one rack unit that's enabling 32 inputs and 32 outputs. Why 32 by 32, you ask? Well, Dante and MADI at 96K is 32 by 32. So we've kind of kept that as the limit for now. One antenna does the job of 3. Coax cable, what's that? Don't know anymore, don't need it. Go find me some network, please. Range extension for IEMs becomes easy because, of course, 4 antenna sockets becomes 4 separate zones. We don't have to think about crazy amplifiers and splitters and all of that sort of stuff. All the audio on the input side, well, in both directions actually, but if we're thinking of multi-mic capturing, as long as you're using the same link mode, all audio is synchronized. So actually from an IEM perspective, we're transmitting 2 completely segregated mono streams that are phase coherent. So your sound stage is open, it is completely in time, it's completely phase aligned. There is no compression, it is completely open in dynamic. On the receive side from your devices, it hits the output at the same time. So if you did have multi-mic capturing, then it is completely phase coherent through the system. Or maybe even stereo, possibly. You could be using stereo playback. Frequency calculations, of course, there isn't any, because it is one frequency and it's now time divisioned. We're not thinking of more spectrum for more channels. It's one block with everything taking turns to use that block. Polite spectrum usage, we get on the edge of range as we can make this go. I mean, that's flashing quickly because it's trying to repair, but that's on the edge of range. It's not currently transmitting until it gets back into range and it goes back to solid. Lower spectral power density, already covered. Distributed interference management, because every device has the soft filter sets and the 2 frequency variants. If you have any more questions about WMAS, then we have had on air for almost 2 years now a WMAS page, thesennheiser.com/WMAS, which is talking about redundancy. There's lots of really interesting articles with development, with spectrum policy, with people like Jonas actually doing coexistence testing, and of course the product page. But that's kind of the end of what I wanted to show you. Are there questions from the room, or indeed from the outside? Was that what you expected to take away coming in here? Maybe. Okay. I haven't got any swag, sorry. Okay. Thanks.